Okay, everybody, good afternoon, and thank you for coming. This session is being taped because I've received about 30 emails in the last 2 days from pilots who want to come but can't because they've been called out by crew control and they've had a roster change and stuff like that. But a lot of people wanted to be here, so at least we'll get this captured and we'll host it on the company website for everybody. So without any more talking by me, I'd like to introduce Steve. Steve just described his title to me, but he's kind of in charge of marketing for Rockwell Collins in the Asia Pacific region, and has been doing similar for a number of years. And Steve has been providing, I don't know how many of you are familiar with it, lots of training material for the WXR 2100 radar we've got on our Dash 8s. But most of the theory behind what he's pushing is just as relevant for the RDR 4000 on the 777 and on the 330. And I see a number of pilots from those aeroplanes here. So thanks for coming. I'll hand you over to Steve. Obviously, Steve's got a bunch of information to present to us, but feel free to jump in at any time with questions, or we'll definitely do questions towards the end. Okay, thanks, Steve.
I do thank you for the opportunity to be here today. It's not a very intimate setting, so it's a little bit more difficult to ask questions. But as Gus said, as interactive as we can make this session, that really helps me out if I can get some feedback from you guys. So please feel free at any time to raise your hand or just speak up and ask a question, and we'll make this interactive. If I ask a question to you, I'll try and give you enough time to respond before I go on to my next item. So as Gus said, I am the Director of Commercial Assistance Marketing for Asia Pacific. So one question that often gets asked is, why is the marketing guy here doing radar training? And so just to give you some background, I flew P-3 Orions in the Navy for 15 years, active duty and reserve. During my reserve time, I went back to college and got a master's in aerospace engineering, and then went and worked with our radar team for about 10 years on this product back at the home office. So 4 years ago, I had the chance to move back to Asia. I'd been in China before that for about 7 years. So I have a lot of background and experience with the radar as far as working with the radar team. Because of that, because of my pilot background and because of working with the radar team, I've actually written most of the training materials associated with the WXR 2100. So I may not know all the answers that you have to your questions that you have on the radar, but at least I know the key people back in our home office who do know the answers, and I can find them out for you. So that's my background. This is kind of what I thought we would go through today. I'll give you an introduction, a kind of a history of the radar, where it's been, where we are today, and where it's going in the future. Then we'll talk about controls, the basic controls on the radar. And for you guys in the from Dragonair who fly in the A320s, I know you guys have this radar on your A320s. The controls will be a bit different. The control head will be different, but the control functions will be the same. And then for displayed, we'll talk about displayed information. And then most importantly, we'll talk about radar interpretation, how to interpret the radar in various situations. We do have a new version of the radar called Threat Track, which does hail and lightning prediction, gives some new turbulence detection capabilities. I'm not going to spend any time on that as far as training goes, because you don't have that in the fleet yet. But when you get that, I'll come back and do that. And I'll give you kind of a brief introduction, because my day job is marketing, so I'll try and convince you it's the world's greatest thing to put it on your airplanes. And then we'll talk, during the course of our time together, I'll spend a lot of time talking about how the radar works, so I'm going to skip that particular section. And after spending about an hour and a half trying to convince you that auto operation is the world's greatest thing, then I'll spend the last 15 minutes or so telling you how to operate the radar in manual. So just don't pay any attention to my last 15 minutes, because I really want you operating the radar in auto as much as possible. So is that agenda okay with you guys? Okay, I got positive nods on that. So let's do a little introduction here. The original multi-scan radar was delivered to Qantas at the end of 2002. And the original multi-scan radar, which forms the basis of the radar you're flying today, took two different beams at two different tilt angles, and it took those two sweeps, and it took all of the ground and weather information in front of the airplane and stored it into a memory buffer. Then inside the radar, there's a terrain table, and we use that terrain table to draw a conformal line to the terrain. And then the magic of this original radar back in 2002 was what the radar engineers called a beam-to-beam power analysis. And they can do a beam-to-beam power analysis and tell if a return right here, because the power of that return changes depending on the tilt, they can tell if that return is below this line or above the line. So anything below the line is eliminated as ground clutter, and everything above the line is left as weather. And so the end result of that was the ability to show the weather from the nose of the airplane out to 320 nautical miles without ground clutter. So that was the original breakthrough in 2002. This was kind of a partially manual radar, partially auto radar, because the problem that you guys told us about was, that's great, I've gotten rid of ground clutter, I can see more than 80 nautical miles in front of the airplane now, but I really have no idea what's a threat and what's not a threat. So I have to go to manual to analyze the weather to figure out if it's a threat or not. So in 2006, 2007 timeframe, we introduced Multiscan V1, which is what you're currently flying right now. And in this case, what we did was we took that same beam-to-beam power analysis, and you can see the gray area up there. We drew a line approximately 6,000 feet beneath the airplane, and we did storm top measurement. And we said, okay, if the cell top is within 6,000 feet of the airplane, then I'll display it. And if it's not within 6,000 feet of the airplane, then I won't display it because it's not a threat to the aircraft. So the idea was the radar would only show threat weather. Well, it's not quite that easy because unfortunately, or just because of nature, thunderstorm characteristics change dramatically depending on where you are in the world. So for instance, a traditional thunderstorm, as you guys know, has a reflective portion that the radar can see, and then there's the top to the cell, the non-reflective portion that the radar can't see. So you have a radar top and you have a visual top, and those two are very seldom the same. Now over the central US or over northeastern India, you'll get very strong updrafts that push the water moisture up very high in the thunderstorm. So actually the non-reflective cell top and the reflective top are fairly close together in that area because of the strong updraft pushing the moisture to high altitudes. However, over the central Pacific, around the equator, those thunderstorms tend to be about 200 times less reflective than a land-based cell is. And so that 200 times less reflective means that you have to look much lower in the thunderstorm to actually find the visible moisture. Now the top still comes up to the aircraft altitude, but you have to physically look lower in the cell to determine where that cell is. So as a result of this, in 2007 timeframe, we incorporated in the radar what we call geographic weather correlation. So we actually have a weather database that resides inside the radar that helps us determine the actual cell top height. So let me explain a little bit how this works. When you're flying around, the radar asks itself three questions. It says, where am I? Where am I physically located in the world? And then it says, am I over land or over water? Because thunderstorm characteristics change depending on that environment. And the third thing it does is it says, what time of year is it? Because obviously these stealth characteristics change depending on the time of year. So if I'm over the central Pacific, the radar may look down at, say, 23,000 feet and says, okay, I see weather at 23,000 feet, but based on the storm models, I can predict that the cell top reaches up to my altitude at 34,000 feet. Pick an altitude. And so the radar will look down at 23,000 feet, say, okay, based on my storm models, I predict you're within 6,000 feet of the aircraft, so the radar chooses to show that what it's seen down here at 23,000 feet, it will show at the aircraft altitude. Does that make sense? I don't see any no's, but I don't see many yeses either. So, okay, you guys got a nod out there at least. Okay, help me out with this. So, now, over the central U.S. or northeast India during pre-monsoon, what'll happen is you may be at 34,000 feet, and the radar may only need to look down at 20 or 30,000 feet, 28,000 feet to determine if the actual top's actually at the cruise altitude. So by setting these different thresholds around the world, what this does is it prevents inadvertent thunderstorm top penetration, and then the goal here is to prevent unnecessary deviations. If I set one threshold and made it the same everywhere in the world, then sometimes I would underwarn and I wouldn't show the cell properly at being at altitude, and many times I'd overwarn and deviate unnecessarily. So that's what the radar is trying to do. By the way, any idea why thunderstorms over the ocean with all that water don't have any moisture in them? That's exactly right, actually, because what happens over the ocean is that you get a constant temperature over the entire surface, and there's no strong uplift motion. It's kind of like a heat sink. Everything is the exact same temperature. Whereas over the land, what happens is you get strong updrafts that are from convective heating and also from uplift over mountains and various things that cause these updrafts that carry the moisture up to really high altitude. So you're exactly right. The updrafts are the reason that you get strong convectivity over the land and less convective weather over the ocean. Okay, so the result of this was what we call our quiet dark cockpit. This is a Qantas 737, and you can see the HUD there. I don't know if you can quite see it. There's a circle along that kind of greenish line up there. The green line is the horizon line. The circle is the flight path vector. And you can see all that weather out in front of the aircraft is beneath the aircraft flight path. And so the radar here shows a clean screen. And that's by design. But this is also one of the major training issues associated with the radar. There are three major training issues associated with the radar, and this is the first one. Because what will happen is you'll see this, a pilot who doesn't understand what the radar was doing will look out the window, see all that weather out in front of the airplane, go to manual, tilt down, and I can get all of that weather to show up on the radar display when I go to manual. I can get it all to show up. And so it's a common write-up when the pilot comes back that the radar does not paint known weather in auto. Okay, but that's by design. If the weather is not in the aircraft flight path, then by design the radar doesn't show it. Does that make sense? Okay. I'll reemphasize this one because, again, it's one of the three major training issues. This one comes up a lot. So multi-scan V1, quiet dark cockpit. Okay, my day job is marketing, so I'll give just a couple of marketing slides here. This is one of the marketing slides. This is a Boeing study that was done on HMI for the 787, and our radar is standard on the 747-8. So Cathay is now a customer of ours because you were forced to take our radar on the 747-8. Otherwise, I'm not sure we would have ever gotten in here. But thank you for that. And so 747-8, 787 standard. This is like I said, a study Boeing did with the multi-scan like HMI, human machine interface. You can see that with the radar showing what's just at the aircraft altitude, you get very efficient flight paths. Now we have a competitor, which you guys also fly, that has a different HMI, and Boeing did the study on that one as well, and you can see it looks like a little like you stepped on an anthill. People kind of go everywhere when you show weather that's both at your altitude and down beneath your altitude. This is version 2 of the radar, and we have some new HMI, these red speckles, which I'll kind of explain a little bit later. But what we do with this version of the radar is we take those normal horizontal scans that the radar is doing as part of the V1 radar that you're currently flying, and the radar tracks up to 48 thunderstorm cores. And then it does a threat analysis and says which of those cells is the greatest threat. And it then does an individual analysis of those cells that are out in front of the airplane. So it'll be scanning along like this, finds a thunderstorm out in front, and it does a vertical analysis of that cell. And it'll stop and dwell on that cell, and it's looking for the vertically integrated liquid content, which means where is the liquid, how high is it, how much is there, how does it correlate with the outside air temperature. It's looking at over 100 characteristics of the thunderstorm to give a real-time evaluation of the cell. And so it looks at growth rate information. So there are a lot of things you can get from that, including hail and lightning prediction and some new turbulence features. And I'll introduce those in a minute as part of my marketing function. Whoops, okay, my last marketing slide, and then we'll go into the training deal. This radar did launch in 2002. Qantas was the launch customer. We have been very successful with this radar in the marketplace, over 200 customers around the world these days, and most, as opposed to Cathay, which you guys were forced to, most chose to take our radar. So, I won't drive that home too much. Anytime you guys want to choose us, please feel free to do so, though. Oh, yes, thank you very much. Okay, you guys did choose for the 777X, so I'm very thankful for that, yes. Okay, so anyway, we have been very successful with this radar around the world and have actually had, for the last 13 years since we launched this product, have averaged over 70% capture rate every year for all the radar competitions around the world. Okay. So let's talk a little bit about controls on the Boeing 747-8. Again, I apologize for the Airbus folks in here, but the controls in your aircraft will have the same function, just not the same control head here. So if you look at the control head on the Boeing aircraft, it does have a nice feature. You have a left and right part to the panel. So the upper left-hand corner of the panel are the captain's controls, and then the bottom right-hand quadrant are the first officer's controls. And so you have independent control of the radar as opposed to the A320 where you have one setting and that's the only thing you can do. So there are common controls on the radar as well, the auto, left and right, and test. So for the auto button, this is where you select auto, manual. When you select this, and when the button is selected to manual, you get an M by the tilt code. And that's how you know you're operating in manual. When you select auto, you get an A by the tilt code. Now the Airbus control panel is actually a bit nicer because the auto manual is actually a switch, so you physically know if you're in auto or physically know if you're in manual. On the Boeing aircraft, you have to look at the ND and see the A or the M to know if you're in auto or manual. Just a note that when you're operating the radar in auto, remember we're taking 2 scans at 2 different tilt angles. So the tilt angle that you're seeing on the ND is actually averaged between those 2 scans. I believe you're all flying dual RT systems, so when you have the left RT, when the button is out on the Boeing aircraft, you have the left RT selected. When the button is in, as that little hat symbol shows, you have the right RT selected. And then there is a test function on the Boeing aircraft as well. Hang on a second. There's a test function on the Boeing aircraft as well. I'm not going to go into the test procedures. In the pilot's guide that I've got a draft copy of that available electronically. By the way, I'll leave my contact information up here, and you guys are welcome to contact me at any time if you have questions or whatnot. But I have a draft pilot's guide that has all of the actual procedures for the test situation. So that's the easiest thing to do, and look at that. If you select test and you get these 2 little icons up here, left or right of the windshield icon, that does mean you have the V2 multi-scan threat track software loaded. We do have a transfer button on the Boeing control panel as well. This is really useful when the radar is being operated in manual, less useful when the radar is operated in auto. What transfer does is it allows you to take all of the other pilot settings and transfer them to your side. So if you're the captain and the first officer has an interesting picture on the right-hand side, you can hit transfer, and then all of the first officer's settings will be transferred to your side, and you'll immediately be able to see the first officer's settings. And likewise, the first officer can do the same. He can hit transfer, and all the captain's settings are transferred to his side. This has especially good use when you're in manual because you can set different tilt settings. And Obviously in auto, the radar's handling all the tilt settings automatically, but in manual you can set a tilt setting for like the 40 nautical mile scale on the right-hand side and a tilt setting for the 80 nautical mile scale on the left-hand side, and then you can get different radar pictures and transfer back and forth that information. Now I will say this, if both pilots hit transfer at exactly the same time, the radar gets very confused. It says, I have no idea what you want me to do now. So when it does that, when that happens, it puts a test pattern up and says, hey, I'm confused. Somebody has to deselect transfer. Maybe not the best HMI interface in the world, but that's the way it was set up. So I did this training years and years ago for Air France, and they said, gosh, we have never, ever hit transfer at the same time, ever. And I went on a jump seat with them down to Johannesburg that evening on their 747-400, and both pilots hit transfer at the same time. So up popped the display. So never say never. You know that, guys. It's you'll get caught. So when you select weather on the radar, here's the design criteria for the radar. The design criteria is to give you weather from the nose of the airplane. When you select auto and weather from the nose of the airplane out to 320 nautical miles without ground clutter, and weather at your altitude. So in this case, you've got a nice cell right here at about 60 nautical miles. You've got one at, 140 nautical miles right here. There's one on the horizon at about 200 nautical miles, and there's one over the horizon at 300 nautical miles or so. And in all honesty, this is easy stuff. This is North American weather. And North American weather is the easiest thing for the radar to show. In fact, we were accused for years of making North American radars. Qantas used to accuse us of making North American radars. And we said, gosh, you just don't know what you're talking about, Qantas. And then when we first launched this radar in 2002 across the Pacific Ocean, that was before anybody knew about these different weather characteristics in the different part of the world. At least most people in aviation didn't know. We launched that across the Pacific Ocean in 2002, and the radar was blind. It didn't see anything. And we said, oh, goodness gracious. We understand your operating environment's very different than what we thought it was. So we did a quick fix to that, but that's where the geographic weather correlation with all the different weather models around the world originated from in the first place. Another reminder, the quiet dark cockpit, you can see all this low-level weather that doesn't affect the aircraft flight path is not displayed. Weather plus turbulence is where you get Doppler turbulence out to 40 nautical miles. And you get that on any range scale. So if you select weather plus turbulence, you get the magenta turbulence out to 40 nautical miles. And even if you select 320, you'll still have the turbulence out to 40 nautical miles, although you won't be able to see much of it on a 320 nautical mile range scale. So it's limited to 40 nautical miles because it is Doppler turbulence, and so you have to have that Doppler feedback in order to be able to present it. When we go to version 2 of the radar, our multi-scan threat track, WX plus T actually becomes weather plus threat, and that's where all of the new threat track features will be located. And these are the 6 different things that will be available in the radar. Again, I'll do my little marketing pitch on that in a bit here. Map mode. Map mode is very similar to the ground clutter mode or ground clutter button. Map mode basically turns the gain down by 1 color level so everything doesn't look red all the time. And what you can get is major coastlines. You can get city. You can see Chicago up there, and you can see some of the highways coming out of Chicago. This is not Google Maps. You know, you're not going to have a really nice, crisp layout. But cities will show up because man-made obstacles are really good radar reflectors. As I mentioned earlier, GC is very similar to map mode, except it's spring-loaded. And this, when you select GC, ground clutter, you'll get ground clutter on the display. Actually, the radar will show everything that's in the memory buffer, the ground clutter and the weather, just like it does in map mode. The reason we put that GC button in there originally was because you got to remember 13 years ago when we launched this radar, nobody was used to a clean screen. Everybody was used to ground clutter all over the place. And so that GC button was in there so the pilot could press GC and you could get ground clutter on the ND, and you say, oh, okay, my radar's working, I feel confident now. So it was a pilot confidence button back in 2003. So we don't really need it anymore because most people are now used to clean screens when they're flying the radar. So I'm trying to get this repurposed. I was mentioning this over lunch, trying to get this repurposed as a look below the airplane type button. So right now, the radar has a cutoff limit about 6,000 feet beneath the airplane. This would allow you to push GC and see all the weather that's in the memory buffer without the ground clutter. I haven't been successful. I've got it on the roadmap, but I haven't got it funded yet internally, so I'm still working on that one. Just a reminder that in auto mode, tilt's controlled by the radar, so you have no control over the tilt during auto mode. I know that sounds obvious, but we had a U.S. airline A330 captain who downed the airplane in Seoul, Korea for 3 days because he couldn't get the tilt to work in auto. So don't do that. It's a waste of your company's money when you do that. Gain control is active in both you have full above and below gain control in both auto and manual operation. And gain is kind of the second major training issue associated with the radar. So I'm going to save that for the next section here and talk a little bit more about that. So our recommended operating procedure for the radar is cal gain. Minimum gain is fully counterclockwise, max gain is fully clockwise, and then our recommended operating procedures are auto, cal gain, and weather plus turb or weather plus threat if you have the threat track software. The other thing is you can tell that you're in cal gain if you have no gain indication here. If you're out of the cal gain position, then you'll get a VAR for variable gain at that point. Any questions on the basic controls? Okay, I have a question for you. It's really tough. In fact, you were very brave. I should always bring the prize for the first guy to answer or ask a question. I forgot today. So, but if you give me your email afterwards or your address, and I've got a great thing to send you. So, it's always really difficult to ask a question, especially in this environment. But I'm gonna ask you a question. Do you know? For years and years, I taught a communications class back at our company. Do you know how long it takes to hear a question and respond to it about? Well, actually, your response time was about right. I mean, nobody actually answered the question, but I got a lot of giggles at that point, and it's about 4 seconds. So your response time was actually pretty good. Do you know how long it takes? You know how long most instructors give you to respond to a question? What? Yeah, exactly right. About 2 seconds. So that's why there's very little dialogue. So not only is it difficult in an auditorium situation like this to have a dialogue, it's also difficult because the instructor's normally thinking about what am I going to say next. So watch your next instructor and see how long he gives you in between questions. So when I go silent up here, it's because I'm trying to count to 4 before I say my next thing up here, just to let you know what's going on. So let's talk a little bit about gain control and what that means. Now, again, the gain control settings are similar for Airbus and Boeing. This is the gain chart for the Boeing aircraft. And again, nobody needs to memorize these numbers. But what you can see is cal gain is 0 dB. A dBz is a unit of reflectivity. It's something the radar engineers use to judge how sensitive the radar is. So 0 dBz is considered the cal gain position. You can see that full gain is plus 16 dB and fully min gain is minus 14 dB. So again, none of those things do you have to remember. Actually, on the Airbus control panel, you guys got a cheat sheet because the control panel actually puts those gain settings on the control panel. So I think it goes -3, -6, -9, And then on the plus side, I can't remember exactly what it goes. But all these numbers are actually on the Airbus control panel. The one thing that is important to remember is that there is 10 dBz between color levels. So when you go from green to yellow, you're actually transitioning 10 dBz of sensitivity. So if you look at this, plus 16 dB in max gain, that's about a 1.5 color level increase in sensitivity. And if you look at minus 14, it's about a 1.5 color level decrease in sensitivity. So what does that really mean in real life? Here's what it means. This is a cal gain setting, and when I go to max gain, plus 16 dB, I've increased my color levels 1.5 times. What that means is all the yellow in this picture in the center here will turn to red. And it means if I'm in the top half of the green, if you look at that green block up there, and I'm in the top half of that green, then it will turn to red as well in the top half of the green. The bottom half of the green will turn to yellow. And then additionally, some of the black areas will show up as green or yellow as well. Does that make sense? Okay. I'm depending on you to raise your hand and say no if it doesn't, because I'm looking at all the positive nods, and so that's helpful to move on. Okay, so if I do to min gain, the exact opposite happens. All my green will disappear if I go to min gain, and in addition, my yellow, if I'm in the bottom half of the yellow, it will turn to black. If I'm in the top half of the yellow, it turns to green. And red will turn to yellow or green, unless you can have 50 dBz thunderstorms, or 55 dBz thunderstorms. So you can go to min gain, and you can still get red on the display in min gain. And if you get red on the display in min gain, man, fly a long, long way away. That is a really scary thunderstorm. It means it's more than 55 dBz, and those are the kinds of things that have tornadoes and giant hails. Man, they're really scary. So if you ever get red in min gain, stay far, far away. One thing to remember is there are times, and I'll explain these in just a bit, there are times when it's good to go to a lower gain setting. What you have to remember is once you've evaluated the weather in the lower gain setting, then you need to go back to the cal gain position. We had one instance of a U.S. airline flying a 777, and the guys went out and the first flight crew went out and they set min gain on the radar. And then the second crew came in, got in to that aircraft, didn't realize the radar was in the min gain position, and immediately took off, flew through a thunderstorm that was painting green on the radar display, but was actually red. Had to come back and make an emergency landing. So don't do that to your buddies. Don't leave it in the min gain position. Go back to the cal gain position after you're done. We talked about VAR when the radar is not in the cal gain position. Okay, so that's traditionally how gain works, and that's in manual mode. Now let me talk about the differences for gain in auto mode with the radar. Remember we talked about the fact that the tops of thunderstorms are non-reflective, and that's kind of one of the basic facts that's true for any radar anywhere in the world. So one of the key things you guys are trying to do when you're out flying is make sure you don't accidentally fly through the tops of one of these non-reflective cells. And we have a lot of procedures we go through in manual. The RDR 4000 has a lot of procedures in their training material to help prevent this. We do a lot in the auto mode with the radar to try and prevent this. But one of the things that we do is what we call automatic temperature-based gain. When you get up to an altitude where the temperature is less than minus 40 degrees C, normally at that altitude, most of the top of the cell is glaciated. It's full of ice crystals. So it's just not going to show up very well. So what that means is at lower altitudes, these big cells, they show up pretty well because you're looking into the reflective part of the cell. Mid-altitude, it can be the same. But at cruise altitude, that's where you tend to run into difficulties because you can actually overscan the reflective part of the cell and be looking through that non-reflective part, and it'll disappear from the radar display even though it's at your altitude. So again, I'll give some hints on how to avoid that in manual operating procedures here at the end. Well, one of the things that we do to help prevent this, I've already mentioned one of those, and that's the geographic weather correlation, where we set different thresholds around the world depending on the storm models that are available. But the other thing that we do is we have something in the radar called automatic temperature-based gain. So as you're climbing and it's getting colder and colder outside, and there are more and more ice crystals, what happens is the radar is automatically turning up the gain. So by the time you're at cruise altitude with the multi-scan radar in auto cal gain and manual max gain are for all practical purposes the same thing. Does that make sense? So there's a lot more gain in auto than you're used to if you're used to flying manual radars. And there's more gain than if you're used to flying the RDR 4000 as well. So here's kind of what it looks like. This is the weather. This is a Qantas 747-400 here. This is some of these non-reflective oceanic cells over the Central Pacific. And this is manual cal gain right here. When you go to auto, or manual max gain, you can see all of these green cores. These are actually the core of the thunderstorm. And they've changed to red and yellow. And then I'm now seeing the edges of the thunderstorm as well. So one of the reasons that we put the increased gain into the radar is to be able to see the full extent of the thunderstorm at cruise altitude. You can see the auto cal gain and manual max gain are very, very similar. Okay, so there's a lot more information. I really like this, but it takes some getting used to, because there's a lot more information at cruise altitude than you were used to in flying the radar in manual. As a result, guys will have a tendency to deviate when they really don't need to. So when we get into the radar interpretation section, we'll talk about how to use this information in such a way that you keep everybody safe, but also avoid unnecessary deviations. So we kind of already talked about this. This is the quiet dark cockpit concept, kind of a bigger picture of the HUD display here. You can see the flight path vector, the circle right up here, and the horizon line, and of course the clean screen. Quiet dark cockpit, as I mentioned earlier, this and the gain are two of the three major training issues associated with the radar. Because again, I can go to manual, tilt the tilt down, and I can get every one of those cells to show up there. And so this is by design that the radar is not painting anything in auto, because that weather is not in the aircraft flight path and not a threat to the aircraft. Okay, this is a great picture I got from Air New Zealand about 3 or 4 months ago. But this is the weather out the aircraft here, or out the window of the aircraft. This is the HUD display right here. And this is the radar return right there. Man, I wish the radar were that perfect every time. I have to tell you it's not, and I'll give you some examples of where it's not and how to deal with that. But on this particular day, that was awesome. I mean, you can see all that weather that's down there, not a threat to the airplane, and the radar just showed what was actually at the aircraft altitude. That was pretty cool. So I have to do my marketing day job as well, you know. So I'm going to show you all the good stuff. But as part of the training, I also want to show you where the warts are, so you can know how to deal with those. Now, it's sometimes debatable whether something should be on the display or not. I'm not exactly sure why, but I get lots and lots of pictures from Air New Zealand, and this is one of them. I think part of the reason is we had a really hard time introducing this radar at Air New Zealand, because they were used to using the radar in manual very differently than most airlines were, so they didn't trust the radar. So this was actually one of those early flights, and we had, in the left seat, we had a multi-scan believer, both captains, by the way, and the right seat was a multi-scan skeptic. And they're arguing about this cell right here, whether it should be on the display or not. And my colleague happened to be in the jump seat listening to this dialogue. So that's what's on the radar display, and you say, okay, I don't really know at this range, I can't quite tell. But then, I mean, right here, you say, my gosh, that's got to be on the display. Why is that not on my display? And actually, when you get right up to this cell, you can see you see the light shining through the back of this cell. During the post-convective time of a cell's life cycle, what happens is that cell rains out, you get water very low in the cell, but what happens is there's just a bunch of fluff left up in the cloud afterwards, and there's no turbulence associated with that. And in fact, you could fly over the top of that at 50 feet and it wouldn't even bounce you at all, because that light shining through that cell tells you it's a post-convective cell. Now, when I said 6,000 feet beneath the airplane earlier, I used the word approximately. And I did that on purpose because the moment I tell you 6,000 feet, you will call me a liar. Because weather is so variable that the moment I tell you 6,000 feet, it will be either more than or less than 6,000 feet. So it's always, I use that word approximately 6,000 feet. This cell was actually about 1,000 feet beneath the aircraft altitude, and it's a post-convective cell. And so this is a correct picture. That is not a threat cell to the airplane. But this takes some getting used to and some building some confidence in the radar that the radar is really telling me what the real threat of the cell is. Because just looking at it wouldn't necessarily tell you one way or the other. So let me talk a little bit about beam characteristics and attenuation and how that affects the radar. Essentially, when the radar looks out at 300 nautical miles, a lot of that radar energy, and this is general purpose, true for all radars, a lot of that radar energy is absorbed by the atmosphere or scattered into the atmosphere. So by the time the signal gets back to the aircraft, the signal that's returned is far, far weaker than the signal that was sent out. So what that means is, essentially to the radar, when it sees a cell out at 320 nautical miles, because of all the attenuation that's occurred, that cell looks green to the radar. We have a very smart radar on the airplane. It says, hey, I know pretty much how much attenuation has occurred over 320 nautical miles. I know you're not green. So we have something in the radar called long-range color enhancement, and the radar says, okay, you're not green, I'm going to make you red. And then it says, hey, pilots, they don't, you got to be careful with those guys. They don't like red blobs, so I'm going to put a yellow thing around it and a green thing around it so you'll feel comfortable that it's really a thunderstorm. So that's what's called long-range color enhancement. So you can pretty much know what the attenuation is. So this kind of shows you the radar is getting the colors right out here at 300 nautical miles. But what happens is, as those cells get closer, notice how they get bigger, because the radar can see more and more of the edges of the thunderstorm. And so the colors stay pretty consistent over that time as they transit in towards the airplane, but they tend to get bigger. Now, I'll talk about it in just a little bit, but one of the other major limitations of any radar system is the radar beam width. So there's no way that you can measure the tops of these cells out here at 320 nautical miles. But if the radar is seeing weather out at 320 nautical miles, it doesn't see little stuff. It only sees big stuff. So it's not unusual for that stuff at 320 nautical miles to track all the way through until it passes behind the airplane. Does that kind of make sense about attenuation? Okay, I counted to 4 and saw some nods, yes. Man, it's much easier when we're all sitting around a table because you get a lot more feedback. But hey, I'm doing the best I can. So, all right, so let's talk about, that's long-range color enhancement. From 0 to 80 nautical miles, we have something in the radar called sensitivity time control, or STC. So sensitivity time control is designed to keep, let's say we had 2 cells that were exactly the same, one at 40 nautical miles and one at 80 nautical miles. This one might look yellow. Let's say that one's yellow. And this one might look green because of the attenuation that's occurred over that 40 nautical mile distance. So what the radar does is, you can see the magenta line up there, it actually increases the sensitivity of the radar over time, so that there's more energy on this long-range cell out here at 80 nautical miles and less on the energy on this cell at 40 nautical miles. And the design goal, it's too far. is to keep the cell looking the same as it transits in towards the aircraft from 80 nautical miles until it passes behind the aircraft. So if you didn't decrease the sensitivity as that cell got closer to the aircraft, it would expand and get bigger and brighter and all that sort of thing. So we do have a limitation in the STC. And if you're following that magenta line up there, we're turning as the cell comes in towards the airplane, we're turning the gain down, turning the gain down, turning the gain down. But at 40 nautical miles, we reach a physical limitation where you can't turn the gain down any further. And so what tends to happen is with this radar in auto is you'll find a deviation path at 80 nautical miles and you'll head up between two cells. And then at 40, it'll fill in with green at about 40 nautical miles. Have you guys seen that? I got lots of positive nods on that. So I used to think, in fact, I was back at our head office about 6 weeks ago, and I was talking to our radar engineers about this, and I said, what I really want is for you guys to figure out how to keep that from happening. Just keep it black all the way through. Because frankly, when it fills in with green right there, it's filling in at zero, it's about a 0 dBz return. If you think about it, that means that's 2 color levels less than the standard green color. So there's really no threat there. What's happening is that the haze layer between the cells is filling in as you get close at about 40 nautical miles because you can't turn down the STC anymore. So that haze layer in between the cells becomes visible. And I'm starting to rethink my idea. It is a training issue, but the fact of the matter is you're going to get light chop when you go through there. So on the 747-8, since you're just hauling boxes, it doesn't matter. But if you're on the A320, you're going to want to turn the seatbelt sign on because you're going to get some bumps when you go through there. So I'm beginning to think that, okay, maybe we leave this the way it is and this becomes something like a turbulence warning. So I'd be happy to get feedback from you guys on whether you think that's a positive thing or not. But anyway, this is a physical characteristic of the radar. If you've chosen to go through this area at 80 nautical miles and it fills in with green at 40 nautical miles, you can still continue through there. And we'll talk more about this later, but in most cases with this radar, green does mean go. Not all, and I'm going to explain what the not all are, but in most cases, green means go. So, does that make sense? Because this is kind of the third major training issue. So, right, so I'm starting to think this is actually not a bad thing. It's a good thing, but you have to understand what it is. So what you don't want to do is drive up to 40 nautical miles, all of a sudden you get green, and then you have to make a last-minute giant deviation. You don't have to do that. You can go through there. And I will say this, for those of you who speak Mandarin, I'm Buhaoisa. I'm really embarrassed to tell you about this, but we do have at about 7 nautical miles, 7 to 15 nautical miles, we've got a blooming issue in the radar where there's a memory function in there that's designed to keep the cell on the display until it passes behind the aircraft, and it's grabbing. Okay, let me kind of explain what's going on right in there. When a radar looks out at weather is variable. So you may get, if you're looking at a green return up here, what happens is that green return, the radar may do 6 pulses, and 5 of those will be green, and 1 will be yellow. And so the radar says, okay, you're green. I'm averaging you to green. But in that last 7 to 15 nautical miles, we have something called overflight protection, which is designed to keep the cell from falling off the display. It's a memory function that pulls the radar, it pulls the weather through at that last little area where it sometimes falls off the display. And that memory function in your current version of the radar is capturing the strongest return. So let's say it does 5 green returns and all of a sudden it gets a yellow return. It says, oh, yellow, I'm going to hold that. And then it does 5 more green returns, it gets yellow. And so what happens in that last 7 miles, it blooms to yellow. There's not much you can do at that point. You kind of have to go through it anyway. That needs to be fixed. This I'm thinking is okay, but that blooming function has been fixed on version 2, and we have a service bulletin coming out that will fix that. That's a major concern to me because it causes a loss of confidence in the radar when you get blooming at that last 7 miles. Anyway, that's why it's happening. I have some pictures of it if you're interested in it. We can show you later. So any questions on this? Okay. And you guys feel comfortable, maybe do or don't feel comfortable, that if you got something like this, I don't need to make a last-minute deviation, right? Okay. So let's talk a little bit about attenuation and why it's important to understand attenuation. This is back in the mid-1990s, one of our wind shear test flights. So our guys used to take a Saberliner out and fly around at 1,000 feet in Florida looking for thunderstorms to fly through so they could get wind shear events. Okay, so their job function's a bit different than yours. So this is one of the events they flew through, and they're headed up through this thunderstorm right here. You can see in the second picture at the top, the middle picture at the top, when they're about halfway through, the attenuation is so bad, there's so much water on the radome that they actually lose major portions of the picture. And then you can't quite see it, but in this top right-hand picture, if you were looking on my computer, there's a little green dot right at the bottom right-hand side of that oval, and that's the first indication that there might be something else back behind this cell. So you can see right here, they're all the way through the cell. They've got a major thunderstorm system behind that cell, plus there's a hook right here, which has sometimes been associated with tornadoes. And this is a potential hail shaft right in the middle there. So they've gone from bad to maybe even worse. So I describe if you fly into attenuated areas, that front thunderstorm is blocking the radar energy. If you fly into an attenuated area, it's a little bit like playing Russian roulette. You guys know that. You put the gun to your head, spin the chamber, and 5 times you're okay, and the 6th time you blow your brains out. Unless you're me. I blow my brains out the first time. That's why I don't visit the casinos in Macau. So here's kind of the classic example. It's a really old example. It's one of the old monochrome radars. It's a DC-9, but it's the classic example of attenuation. So there was a DC-9 in 1977, and they were looking for one of these through a flight path through this long line of thunderstorms over the eastern United States. And they thought they saw, they had a kind of a narrow path right here that they could get through. And you can see the conversation between the captain and first officer. The captain is looking at the radar display. The first officer is flying. And so they're headed south, and the captain says, "You're all clear left now. I think we can go now." And the first officer says, "Okay, here we go." And this is what they flew into. It was a thunderstorm. Remember we talked about those 55 dBz cells? It was more than a 55 dBz cell. It was a 55,000-foot thunderstorm, and it was producing tornadoes and 3-inch hail about that big. And it shattered the captain's and first officer's windscreens, flamed out both engines, and they tried to glide to an airport over here, didn't have enough altitude. Somewhere in this area, they broke out of the clouds and tried to land on a highway up in the mountains, and they hit a flyover or an overpass, destroyed the airplane, and only the flight attendant in the very back seat of the airplane actually survived. So again, this, 9 times out of 10, 5 times out of 6 if it's Russian roulette, you may be okay flying through that attenuated area, but the 10th time could really be disastrous. So we do have something on the multi-scan radar called path attenuation, correction, and alert. So let me kind of describe what the radar is doing in auto mode. When you have the radar selected to auto and you're in cal gain, what the radar is doing is it's doing its normal scans, unless you guys will have to use your imagination. I normally use water bottles, but it won't work too well up here. So I'm going to have a thunderstorm right here, and there's another thunderstorm right back here behind it. You guys got that mental picture, okay? All right. So I'm scanning back and forth right here, and when the radar gets to this first thunderstorm, it says, "Ooh, there's a thunderstorm there," and so it automatically turns up the gain, the sensitivity, so that it can see better back behind that cell. So it keeps the proper energy on the cell back behind. It does that for every single radial that it goes through. So let normal gain, normal gain, normal gain. Oop, I'm going to turn it up here and look back behind here. Does that make sense? What the radar's doing? That's called path attenuation correction. And then there's the alert function. If the radar is scanning like this and it gets to this thunderstorm and it increases the sensitivity and it says, man, I can't get enough sensitivity to properly display this cell back here, then it puts that yellow bar on the outer range scale to warn you that that it cannot see through that thunderstorm. Have you guys ever seen the pack alert bar? Has anybody seen it? Good, I got one. And normally in a group this size, you get about one person who's seen it. And there are a couple of reasons for that. The first is, look at the extent of the cell up there. This is a 50 nautical mile deep cell. So the radar doesn't attenuate very often. And it's not a major issue with this radar. But the other thing to remember is, though, that you have to be in cal gain, you have to be in auto, you have to be in cal gain, and this is tied to the sensitivity time control. So the thunderstorm has to be within 80 nautical miles of the airplane. And when those three criteria are met, if the cell is blocking the radar energy, then it puts that yellow bar back there. So you can see here I'm in cal gain because there's no gain indication. This is actually an EVA 777 right here. Guy sent me the pictures. And when you go to variable gain, when you're out of the cal gain position, notice that the yellow pack alert bar has gone away. So, man, perfect for training. He took a series of picture here. When he went back to the cal gain position, there's the pack alert bar again. Does that kind of make sense? So it's a very nice safety feature. Only works in auto. I used to think it worked in manual. It doesn't. Okay, I just learned that a couple of years ago. So, all right. Okay, I mentioned earlier that one of the major limitations of any radar system, whether it be the RDR 4000, the RDR 4B, our old WXR 700, or the multi-scan radar, is beam width. So the radar beam is about 3 degrees wide, which doesn't sound real wide, but if you look out here at 320 nautical miles, by the time you get out here, the radar beam width is actually 22 nautical miles wide. I mean, 3 degrees over 320 nautical miles, and you have a 22 nautical mile wide beam width. So you can't measure anything out at 22 nautical miles. Even at 80 nautical miles, the beam width is 28,000 feet wide. So, as I mentioned earlier, we try and we can't measure storm tops out here at 320 nautical miles, but generally if you see weather out at that range, it's really big stuff, and it will potentially pass through behind the airplane. What the radar starts to do is, the multi-scan radar starts to measure the cell tops at 120 nautical miles with a goal of having accurate deviation information by 80 nautical miles, okay? So, however, what that means is sometimes you'll get weather that's a bit indistinct like that in the middle right there, and as it gets closer to the airplane, you see it falls off the display just because the radar can better determine whether it's at the aircraft altitude or not. So there are a number of reasons for this. Remember, you guys, anybody know what the average life cycle of a thunderstorm is? Just a normal air mass thunderstorm, how long does it last from beginning to end? Yeah, perfect, 60 minutes. It's about 60 minutes, 1 hour from beginning to end. And so think you got about 45 minutes of travel time on a 320 nautical mile range scale. So it's not unusual for stuff to die out and spring up. Now it may happen because the radar can better show determine the cell height, but it may just be happening because it's the normal life cycle of the cell. Does that make sense? Okay. See, I didn't give you time to answer that one. I just went right on. So even when I know what I'm supposed to do, I don't always do it. Okay, we do have some instances, I have seen some instances where where the weather radar has made an improper decision beyond 80 nautical miles. These are from Air China, and at the numbers up here, I don't think you guys will be able to see it, but 4, 5, and 6 numbers up here, there's actually a little bitty green dot. And there are some thunderstorms there that are right at the aircraft altitude. And beyond 80 nautical miles, the radar thought that they were beneath the aircraft flight path. And then you can see here, coming on the display here at number 4, at 80 nautical miles has actually transitioned into a thunderstorm cell. So this is not the best. So one of the problems with our radar is that it's got a negative fail. When we goof, you guys are going to know it. You know, one of the nice things about our competitors' radar is it shows everything. So when they goof, you can't always tell. So it's you know, from a marketing point of view, they probably did a better job on that one. So anyway, this does happen from time to time where you'll get a cell that all of a sudden seems to pop up out of nowhere. And here's 4, 5, and 6. So all 3 of those cells were at the aircraft altitude. And by 80 nautical miles, the radar knew that. And again, it met the 80 nautical mile deviation criteria, but it would have been better for him to show them further out. Okay, this is just by the way, I love to get pictures from folks. Gus Lorard's been really good about sending me stuff. And just one warning, if you send me pictures, they probably will end up in my training material. So this is from Captain Meng at Shandong Airlines in China, sitting on the taxiway. Oh, by the way, I didn't mention this earlier, but these current digital radars are very, very safe. What are your guys' procedures for when you actually turn the radar on? When do you do that? Before taxi? On the taxiway, okay. Yeah, so I recommend, you know, turning the radar on as soon as pushback's over and as you're headed out. And this will be one of the reasons why right here. But one of the questions that often comes up is the radar have a radiation hazard? And we did a test where we put a measuring device, took the radome off, put a measuring device about half a meter in front of the flat plate, and then did the normal scanning, and went to max gain, max range, which puts the most energy out on the radar. And you get about half the microwave energy 18 inches in front of the antenna than you do standing in front of your microwave oven. So don't go do that just to test me out. But it is actually safer to stand in front of the radome than it is to stand in front of your microwave oven. So you're not going to fry anybody in the airplane ahead of you. Now, we used to have these old parabolic dish antennas with the magnetrons. Those are what we flew when I was in the Navy. And they put lead walls back behind those radars to protect you from radiation. They don't have to do that anymore because of the low radiation hazard. But here's one reason that it's good to have the radar on during taxi. He's taxiing out, and this is the only time I've ever seen this, but he gets a wind shear alert. And you can actually see the wind shear coming down the taxiway, kind of ill-defined down there. But this is in the form of a line squall coming down towards the airplane. And then it just engulfs the airplane. So he may not like our radar every day, but he liked our radar that day. You know, so on that day, he really thought we had a great radar. He waited about half an hour till the thunderstorm passed beyond the airfield and then took off.
Steve, I'll send you one picture, sorry, but I'll see the day with our 747 crews, sending just like that. At the 11.07 moment, I think, in Hong Kong. Exactly the same sort of thing.
That's pretty wild when that happens. So, yeah.
And decided not to go flying.
Yeah, always good to find that out before you're actually airborne. So there are criteria for when wind shear is activated and when it's not activated. That's in the the draft operator's guide that I've got, so I'm not going to go into that in detail today.
Sorry, can I just ask, the pop-up thunderstorm that comes up in automatic and have everything that we haven't seen in the last set. If I was in manual, I could tilt it down and see that somewhere, correct?
That is correct. Yeah, you would have been able to see that in manual. And I mean, you guys have to tell me, because you fly the radar every day. I jump seat occasionally. I get back on our company airplane, but most of what I put up here is feedback from you all. I don't think that happens very often where the weather shows up late like that. I wanted to put it up there so you know it does happen, but I don't think it happens very often. Would you guys agree or not agree with that? Okay. All right. Well, let me know as time goes by. But I've only now. I don't have contact with everybody. By the way, I have an email list of about 300 pilots around the world that I've had a chance to give this radar training to over the years, and I put periodic updates out. So when I get something like this from somebody, I'll correspond or talk with our radar engineers, come up with a response, and then I put it out to all 300 pilots. Because normally if one person has a question, everybody has the same question. If you'd like to be on that list, then I'll put my contact information up here afterwards, and please feel free to put your name on that list, and I'll make sure you get copied on it. That's been a real good avenue, be able to give information on the radar, but also to get information from you guys about how the radar is performing. So the question, by the way, for the recording was, if I went to manual, could I see that? And the answer is yes, I could see it if it popped up late in auto. Okay, so we're about an hour through. We're doing pretty well on time because there's not a lot of questions going back and forth. So if you guys are okay with this, I think I'll just keep going. We probably will finish about half an hour early, and then we can stop and have questions, or we can have individual questions after everything is done. Is that okay with you guys? I'm always a little leery of given a break right here because I'm never sure how many people will actually come back. So I normally give a break at this point, but since we're ahead of schedule, I think I'll just keep going. So radar interpretation is probably our most important section. How do I interpret what the radar is telling me? And a lot of times with this radar, it will depend very much on how you've used the old manual radars as to whether you think the radar is under warning or over warning. So again, this is Air New Zealand, and they fly our radar on their 777s and their A320s, and because they fly in oceanic areas with very low reflectivity, their manual operating procedures were to do a very aggressive down tilt and max gain. That's how they flew the radar. So this is what they were used to getting on their radar display, and then they got multi-scan and they got this. And they said, man, your radar is not safe. We cannot fly your radar. We don't like it. So we spent several months down there talking with them, trying to help them understand what the radar was doing. And we eventually they got a situation like this on their 777, and they put the carts away. They got all the flight attendants to sit down. They got all the passengers buckled in, and they flew right over the top of that, and they got light chop. And they said, oh, maybe we can trust your radar. So this is the very tip top of some low-lying weather down below. You are going to get light to moderate chop when you go through. It can be uncomfortable. It's worth turning the seatbelt sign on for, but green was okay in that particular instance. But they initially felt like the radar was under warning. Then we went to Thai Airways on their 777, and they fly one of our very old radars on some of their 777s. In fact, it doesn't even have a gain control. So they were used to green being a thunderstorm core over the middle of the ocean, and green was really scary. Green meant I need to avoid you by 25 nautical miles. So when they got the multi-scan radar, this is what they saw. They said, my gosh, there's no place to fly. You've taken all my ability to fly the airplane away. So what I would say is, you know what? My flight path in this picture and my flight path in this picture, they don't change. You can see the wind vector up in the left-hand corner. So the best path to avoid the weather in this case is about 25 nautical miles to the left of that green core. Well, look, in this picture right here, that green core is now yellow, but the difference is now I can see the edges of the cell. And so if I deviate 20 right along the edge of that cell, I'm deviating exactly the same flight path. But now I just know where the edges of the cell are, whereas previously I didn't know them. The other thing I would say is, you might be tempted to go up between those cells because these are oceanic cells, and oceanic cells tend to be less convective than land-based cells. You might still be tempted to do that here because these are kind of normal oceanic cells. If I had limited deviation capabilities, I might still go up between those two cells. But I no longer want to go downwind of that cell because there's a lot of activity downwind of that cell. So I have a lot more and better information, but if I'm not careful, if I'm used to this, I'll deviate way out of the way unnecessarily. Does that make sense? You guys, have you guys seen this real time? If I don't hear anything back, I'll assume that's, yep, I have, no problem, okay? So another example here, manual cal gain. Manual cal gain, and I've got a clean flight path right up the center there. So this is manual max gain. This is Gulf of Thailand. Gulf of Thailand, Bay of Bengal are two of the hardest areas in the world to properly display weather because you'll get significantly building cells that rain out at very low altitudes. So it's really difficult to properly display the actual top of the weather. So you can see in the Bay of Bengal, the radar is actually, or Gulf of Thailand, the radar is actually a bit more sensitive than even manual max gain in order to get the best possible display of the weather. So the best route of flight was right up straight ahead, and I would say the best route of flight is still right up straight ahead. There's some low-lying weather down beneath the airplane. You're going to be clipping the very tip top of it, but that means light to moderate chop. So it's worth turning the seatbelt sign on for, but you don't have to deviate for it. Does that make sense? So I had the pilot who actually sent me these pictures, who I won't name, said, I like this picture. And I said, well, okay, but here you got the chop anyway. He said, here I can fly where I want to fly. I said, well, yeah, but here you got the chop. You just didn't know it in time to turn the seatbelt sign on. Now you know it in time to turn the seatbelt sign on. So it's more information. So, okay, let's talk a little bit about reflectivity at different altitudes and what does green mean. So right at the freezing level, there's an area called bright band. And bright band occurs because ice crystals, they melt, they get coated with water, and for 2,000 to 3,000 feet beneath the freezing level, you get a very strong return because those are really strong radar reflectors. So if I happen to be, this is a vertical radar display right here, and if I happen to be flying, I can't reach that high, so I'll be flying right through here. If I happen to be flying right through here, and my radar is pointed right through here, my whole display will turn red. And I've seen this. Actually, that picture over there is a snowstorm by Boeing Field on a KLM 777. And what's happening is the radar is pointed up because it's down pretty low and it's pointed up. So at the closer range, it's pointing through this yellow reflective region, and at longer range, out at about 7 nautical miles, it's pointed up into this green area. And that's why it changes colors like that. So I've seen at Indigo during monsoon, the guy showed me a picture on his iPad, which I didn't get, unfortunately, but that whole display turned red during monsoon because there's just so much water out there. And so what do you do with that? Well, we'll talk about that in just a second. Normally at low altitude, what green means is just stratiform rain. So if you get a broad area of green at low altitude, that's just stratiform rain. And you can fly through this and it just washes the airplane off at low altitude. Now, if you do get a redout situation, this is the time I would suggest you use gain control to help determine if there's a threat or not. So on the Boeing aircraft, if you go -4 clicks counterclockwise, that's 1 color level. If you go -9 on the Airbus control panel, that's 1 color level. So if I turn the color level down 1 color level, all my yellow goes away and I'm left with green. So let's say I had a strong cell in there that was yellow, or let's say I had a strong red cell in there. Let's say I was in monsoon and I had a strong cell and I turned the color level down 1 color level and it went yellow, then that strong cell would still be there as a yellow cell in the midst of the, if I turn red to yellow, let's see, It might go to green. So let's say it goes to green and I still have a yellow or a red cell there. That's how I tell if there's an embedded cell in that red out area. Boy, I made that complicated for myself. Did I at all make sense on that one? Okay, turn the color level down one color level. How much is one color level? 10 dB, that's exactly right. One color level is 10 dB. So go to -9 on the Airbus control panel, go to four clicks counterclockwise on the Boeing control panel. That's one color level, and if there's a strong embedded cell, that will stay on the display at the proper color. Now, if I'm at cruise altitude and I get green at cruise altitude, that is an indication of high altitude icing. So the picture, the threat changes between low altitude and high altitude. I know you guys fly the high bypass engines on the 747-8, and those are susceptible to the high altitude icing. So every single report we've gotten back has said the aircraft has been flying in green when those icing conditions occurred. So what'll typically happen is you'll get an ice cloud up at altitude, and that ice cloud just kind of moves with the airplane. So what happens is, because we're using the increased gain in the radar, the automatic temperature-based gain, it's being able to see the ice cloud, but it can't see the edge of it. So the radar can give you an indication that there's icing conditions possible, but it can't tell you an escape path because it can't see the edge of the green because of the attenuation. So that ice cloud or that green haze just kind of moves with the airplane. Does that make sense? Okay, so if this happens, you should go, Boeing has a procedure where you go to manual, look down beneath the airplane, and look for yellow or red returns down low, and then you have to avoid it by how many miles? 50 nautical miles. So one of the first things that I would do if I get into an area and I'm at cruise altitude and I'm in this green haze that moves with the airplane, I would activate that Boeing procedure to check and see if there was anything beneath the airplane. This is a KLM this was an Alitalia 777. Same kind of thing. You can see this is one of those giant ice clouds. They got about halfway through. They got TAT anomalies. The TAT anomalies ended once they exited the ice cloud. They did have engine damage on this particular flight. And this just shows some of the research we did that shows that this green haze has been visible every time this has occurred because of the increased temperature, the automatic temperature-based gain. Okay, a little bit more about, so I said in most cases green means go, but not always. So when does green mean go and when does green not mean go? So in this case, green means go. This is the top of some low-lying cells or a low-lying line of weather down beneath the aircraft. And I am going to get light to moderate chop when I go through there. It can be pretty uncomfortable. As a passenger that flies you guys a lot, I know it can be pretty uncomfortable. But the fact of the matter is it can be transited. And so it's worth turning the seatbelt sign on when you get something like this. So green's okay in this instance. Green is not okay in this instance. In this instance, you've got shear effects coming out of this major thunderstorm cell right up here. And this area right here in between is actually a potential hail shaft right in there. So when you get a major convective cell and you have green that protrudes out like this in these fingers, that's something to be avoided. So green is okay. In that case, when it's associated with a shear effect coming off of a major cell, green is not okay. So the radar has a lot of automatic features in it to protect you, but you still have to use your own experience to properly interpret the weather. Does that make sense? Okay, so, as a radar manufacturer, what we say is, always avoid all thunderstorms by 25 nautical miles, upwind side by 25 nautical miles. And in many cases, you would never fly your airplane if that were the case. But that's the legal thing we do to make sure we don't get in trouble. So, however, when you do have to pick your way through a cell, how best to do that? I would describe these as normal thunderstorm cells right here. This is actually a 787 on route proving over South America. And you can see this is the cell out the right side of the airplane. It seems to be breaking up. But a normal thunderstorm, a normal average thunderstorm, is oval or circular in shape. And also you can see the gradient. It goes green, yellow, red in kind of nice big chunks. And so that indicates that, yeah, I'm not going to fly through it. It's a thunderstorm, but it's not overly dangerous. So in this particular case, the pilot chose to deviate right up through here and was able to do so without any problem whatsoever. That's a normal thunderstorm. This is an abnormal thunderstorm. This is this is our test airplane. I was on this flight on this particular day, and you can see you can see the fingers coming out at the top and bottom of the cell. Also, these U shapes in here are potential hail shafts in that U shape area in there. And the green, yellow, red, you see how fast it goes green, yellow, and red? Man, that's a scary cell when it does that, because that means it's a very intense uplift in that cell. So there's a lot of turbulence associated with that cell. We're at about 7 nautical miles, and that's really too close to that cell. In fact, my buddy lives right under that top U-shaped area right there, and I had breakfast with him the next morning. He had hail all over his lawn the day before. So I know that that one was producing hail on that particular day. So normal, abnormal, normal transit when you need to, stay a long way away from. Does that make sense? And this would be true for this particular interpretation is true for any radar system. Okay, so let me talk a little bit about some warts in the radar that have become obvious here of recently. So we do have, we've already talked about the fact that the radar is very sensitive, and we're doing a lot to keep you from flying through the tops of those non-reflective cells. We're doing the variable, we're doing the variable temperature-based gain, the automatic temperature-based gain. We're doing the variable thresholds around the world so that we look at different altitudes for the water, but all of those returns are built around this average cell reflectivity. So, and again, it's difficult because that average cell reflectivity changes depending on where you are in the world, the time of year, and if you're over land or over water. But if you had the radar perfectly centered on this average cell reflectivity, you would overwarn sometimes and you would also underwarn sometimes. That's just the nature of a bell curve. So what we've actually done in the radar is we've essentially, by using gain and these thresholds in different manners, we've actually moved the bell curve right a little bit because we'd rather overwarn than underwarn. So there are cases. I don't think they happen often. I've seen them, but I have seen them. I saw one in India. Well, I've just got a report from one from Air New Zealand on their 787, where the radar, and it can specifically happen over the Asia Pacific area, because after a typhoon, you'll get a broad, bright band area of moisture that just kind of hangs in the atmosphere, and it's a lot of water just hanging in the atmosphere. The radar actually has something in it that when it sees this broad band of moisture, it'll turn the color down from yellow to green, but we don't turn red down. We've never turned red down. So in the case with Air New Zealand the other day, they had a broad area of moisture in the atmosphere with some embedded cells in there, and it was all painting red, and so it was overwarning. And so what the pilot eventually did is he turned the gain down by one color level. The red turned to yellow, and the embedded cells were then visible, and he could pick his way through the cells. Does that make sense? Okay, so the temptation is always to go to manual in those instances. And I would like to avoid that if all possible. Instead of going to manual, use the gain as your control for picking your way through these cells. Here's kind of an example from our current multi-scan threat track software. In the threat track software, this is the V1 version of the radar that you're currently flying. In the V2 or threat track software, we have two different features in the radar. One is called I forget what it's called. I'll tell you in a minute when we get to that page. The other one is a hail and lightning prediction here. But this one feature looks at the convective nature of the cell, and if it sees the cell as more convective than actually represented here by these yellow dots, it turns the color up to better represent the actual convective nature of the cell. Then for moderate cells, when these red dots are within the boundaries of the cell, that indicates these are moderate cells. They're not giant, really threatening cells, but they do have significant lightning potential. So in this case, yellow really does mean caution. This is not really a true overwarning situation. This is really a yellow means caution type situation. But to pick your way through, the best way to do would be to turn the gain down by one color level. And then the yellow will turn to green and look more like this, but you'll still have all the threat track information. Okay, any questions to this point? Okay, now I'm going to tell you some things the radar is not doing as well as it should do. And one of the problems we're having, we introduced SB7, SB503 into the radar, and that does a lot of nice things. For the Airbus people, there was an FCOM that required +4 gain below 20,000 feet. When you install SB503, it does away with that requirement. You can use auto gain or cal gain during the entire flight. However, one of the unexpected consequences of introducing SB7, SB503 is that the radar has gained an oversensitivity during oceanic flight. And this is frustrating to me, and as it is to other people who've experienced this. We are in the process of evaluating this. We'll get it fixed and come out with a service bulletin at some point to get rid of this. But here's the way it shows up. You can see this is over Bay of Bengal. This is from Thai Airways. You can see the stratiform weather down here, and it shows up on the display as kind of green blobs. And those green blobs come in towards the airplane in this kind of situation. They stay on the display till about 35 nautical miles, and then they fall off the display. So that's an overwarning of the radar in oceanic flight. Now, what I would say in this particular instance is that, you remember, green means go, so it shouldn't, the fact that the radar is overwarning in this situation shouldn't cause you to deviate unnecessarily. Just monitor it, and if it falls off the display at 35 nautical miles, you'll know that the radar is overwarning. Okay, it does become a little bit more difficult in some instances. This is, I think, this is either a Silk Air flight or a Singapore Airlines flight I jump seated on, but you can see I've got a cell out here ahead of the airplane, and it's not real big, and you can't really tell at long range whether it's at the aircraft altitude or not. But what happens is, as it gets in closer to the airplane, notice that it gets progressively less intense, and then at about, again, 35 nautical miles, it falls off the display and disappears. So what I would say is, for these single cell ocean, when you have these single cell encounters over the ocean, you got 10 nautical mile RMP over the ocean. So if that cell is on your flight path and it's coming in towards the airplane, just monitor it. And if it starts decreasing in color at about 60 nautical miles and progressively decreases to 35 nautical miles and disappears, it's not at your altitude. It doesn't need to be avoided. Does that make sense? Okay, it's always embarrassing to have to pull up the warts, but I want you guys to know what the radar is doing in these instances. Now, so those two instances are pretty straightforward because one is green that disappears, one is single cells that disappear. The difficulty, and this is from Emirates, is when you get a line of stuff like this off at a distance and the whole thing paints red. And so what you're tempted to do is ask for deviation way out ahead. And then what happens is, as you get closer, you can see these cells. Some of these cell tops are really at your altitude, but you don't really know which is which until about 40 nautical miles. So again, that technique I mentioned for determining if something is oversensitive or not, or if you have an oversensitivity condition, turn the gain down by one color level. So here, turn the gain down by 1 color level, the gaps will show up in the cells, and if the gaps show up in the cells, you can be fairly assured during this oceanic flight that those gaps will appear at about 40 nautical miles. So you can go back to the cal gain position, and at about 40 nautical miles, the gaps will appear, and you'll be able to make your way through the cells. Okay, so this is the most difficult of those 3 scenarios because you actually have to do something to figure out if you need to deviate at that 80 nautical mile point or not. Does that make sense? Okay, we got to get this fixed. I don't like this, but it is currently in the radar. So I don't want to end on a negative note, so I want to show you something that's really, really cool right here. This is a Singapore Airlines A330, and in this particular case, he's got one of these little bitty oceanic cells at 120 nautical miles, and watch, at 40 nautical miles, still can't see anything out the window, but notice, in this case, at 120, at 80, at 40 nautical miles, the cell has stayed really consistent in color, and then at 20 nautical miles, that's the first time you can see something out the window right there, and there's that little bitty cell right up there, and eventually they deviated about 2.5 nautical miles. But these little bitty oceanic cells that poke up like this, I mean, these are really difficult to show up properly on your radar. And so if you're in manual operation and you had the tilt set properly, these would normally fall off the display at 40 to 50 nautical miles. And for the radar to be able to keep this in all the way until it passes behind the airplane is pretty awesome. So we do have an overwarning situation, but the radar is doing a really nice job of keeping the stuff on the display that it should keep there. Okay, so I had to end in a positive note because my day job is marketing. You guys remember that. So, okay, any questions on that? Okay, let me do 5 minutes of threat track marketing. Get you guys to buy this from us, and then I'll switch. After telling you how great auto is all the way through here, I'll switch and talk about manual operating procedures. So threat track, like I said, WX plus T becomes weather plus threat. On the Airbus control panel, the turb function becomes a WX plus T plus hazard switch. And there's 6 new features related to this. Core threat analysis is the name of the one I couldn't remember. Core threat analysis does that analysis of the thunderstorm I mentioned earlier. If it finds that the cell is more convective than actually displayed, it will put, what it does is it changes the core color to better represent the actual threat. You can see that you can see that it's done that in this particular case. This is the ground-based radar, and it better represents the actual threat. Now, at this point, we only turn colors up. We don't turn colors down. Next step, but as you guys know, we've talked about this, you can have these red out situations at low altitude. The next step is to turn the colors down, because the radar can do that too. The radar can automatically turn that color down in a red out situation and keep the core color without changing the colors of the cores. It's just a lot harder to certify a radar when you're turning the color down than it is. It's pretty easy when you're turning the color up. So that's core threat analysis. This may be the one I like most. Thunderstorms can grow as rapidly as 6,000 feet a minute, and when they do, they put this turbulence bow wave above them. So you can get severe turbulence even though the cell is significantly below the aircraft. So the radar now looks down beneath the aircraft, looks for these cells that are growing, and if it finds one that's growing, if it finds one that's growing, it puts a predictor on top of it based on the growth rate. And if your airplane is going to intercept that predicted area of turbulence, then it puts this icon up on the display to say, even though there's nothing at your altitude here, I predict severe turbulence at that point. So you're not going to see this often. This should be like a wind shear indication. It'll only happen every once in a while, but it does happen. Here's the first indication of it. This is a Air New Zealand Boeing 777, and they're somewhere southwest of Guam. And in this case, they could look out the window and the cell was about 10,000 feet beneath the aircraft, or appeared to be. That cell is actually still at their aircraft altitude, but this other area was about 10,000 feet beneath the aircraft, and the radar indicated that it was a growing cell growing into the aircraft altitude. We do have two-level turbulence indication on this radar as well. Solid magenta is severe turbulence, and speckled magenta is ride quality. The hail and lightning prediction is actually based on the life cycle of the cell. Beginning of the cell cycle, end of a life cycle, really not much threat from a cell. We talked about the post-convective cells earlier. The real threat first comes with these small cells around the freezing level. They're not giant cells, but they get electrified around the freezing level, and they can produce lightning strikes. And then, of course, the ones we really want to avoid are the severe cells. So, what does the radar do in these circumstances? Let's go through this. Like I mentioned earlier, for these small cells around the freezing level, and by the way, about 80% of your lightning strikes occur within 3,000 feet, plus or minus 3,000 feet of the freezing level. Best way to avoid a lightning strike is stay as far away from the freezing level as you can most of the time. So if a cell is electrified, one of these small cumulus cells is electrified, the radar puts red dots inside the cell boundary to tell you that it has an 80% probability of being electrified and has lightning potential. So the best way to avoid the lightning strike would be to stay closest to the non-electrified cell. These go away when you're more than 10,000 feet above the freezing level because those cells aren't dangerous at cruise altitude. Then the next thing we do is for a mature cell, these are the giant cells that have strong turbulence, hail and lightning potential outside the cell boundary. We put a red speckled area around the cell to indicate that's a mature cell. And that one over there, right here, actually has a pack alert behind it too. So that's one you'd really want to stay a long way from. And then finally, the last thing the radar does is, oops, this is it. What'll happen is you'll get these giant thunderstorms, and this is the downwind direction. Hail gets thrown out the top, and then in the downwind direction under the anvil. So what the radar does is above 25,000 feet, it has access to the upper level wind information. So that red square that designates that as a mature cell, it rotates the red cell, or that red square aligns it with the wind vector and then extends the red cell, the red warning area downwind, depending on the velocity. If it's a big velocity, it extends it down further. Shorter velocity extends it a shorter distance. Basically, it's reminding you to deviate to the upwind side of the cell. Okay, so that's threat track. If you guys get that someday, I'll come back and tell you how to use it. And like I said, we've spent a lot of time, and I've kind of covered most of the items on how the radar works. If you're interested in more details on that, I've got a chapter. This kind of teaches through the draft pilot's guide. So I'll be happy to send that to you. But I'm going to skip that for today and spend our last 15 minutes on manual operation. Okay, so it is always a little embarrassing to spend all this time telling you the radar is so great in auto, use it in auto, don't go to manual, use the gain if you have any trouble with it, and then spend the last 15 minutes telling you to use it in manual. But here we are. So, okay, so manual operation. In manual operation, tilt is everything. The difference between a good radar operator in manual operation and a not so good radar operator is the use of tilt. If I get the tilt too high, I look up in that non-reflective part of the cell, and I'm not going to see the proper threat to the weather. If I get the radar tilt too low, then I bury the radar in the ground clutter and I can't see the weather. So I'm actually looking for a compromise between too high and too low. So what tilt settings do I use? Below 10,000 feet, oh gosh. Hey, hang on 1 minute. I missed something in here. I'm going to go back and get it because I think it's important.
I guess while Steve's looking that up, Steve referred to his emails that he sends out to group of pilots. Whenever we get one of those, we post that for anyone to see. And we assimilate and combine some of the guidance material he's got time to time, so it's all available on Yammer. We'll probably refer to it in the newsletters as well. But anyone's welcome to contact you with stuff directly too, obviously. But in any case, we'll always continue past those segments.
Great. Okay, so somehow when I was updating this presentation this morning, I dropped out this section on the Boeing presentation. So I did want to talk about non-reflective weather at intermediate altitudes, and this is really a key factor for any radar system. The fact of the matter is, one of the limitations of radar is that you have to have moisture in the cloud in order to be able to properly detect the weather. So in this instance, this is from a Thai A330. The cells are up to about 10,000 feet, and they don't show up on the radar display because there's not enough moisture in them. These are really bumpy. I mean, when you fly through, where you're seeing the cloud, you're getting an updraft in between as downdrafts, and when you fly through there, it's going to be really bumpy, but it just doesn't show up on the display. Here are a couple of examples. This is an Indigo A320 flying out of Bangkok. Another problem is when you're flying in areas with high pollution, those little bitty particles in the pollution, the aerosols, they tend to form a cloud without much moisture content whatsoever. So you can get a major buildup that has very little moisture in it, and it in the case is worsened in polluted areas. So you look here, and out the left side of the radar, left side of the window is painted just fine, but up front, these cells were up to about 20,000 feet, and there's nothing in front of the airplane. And so if the radar's painting properly off to the left, but not painting the stuff up in front, that's 99 times out of 100, that just means that cell out front doesn't have enough water in it to show up. Now there are occasions where you'll get a damaged radome in one particular sector, and it'll get full of water or it'll be patched. So if this happened time and time again on the same airplane where it consistently didn't show weather in one particular sector, it'd be worth checking the radome for. But in most cases, it's due to the fact that it doesn't have much water. Again, this is a Thai A330. You can see the radar shows the stuff in the back pretty well, but this cell right up here at the front right doesn't show up at all. Even when he went to max gain, that cell right up front didn't show up. So if the radar is painting the cells back behind this cell, the only explanation is that cell doesn't have any water in it. Otherwise, it would have to show up in that instance. Does that make sense? Okay, I wanted to show that because that's important, and that affects all radars. Okay, so back to the manual operating procedures. Sorry, I got things a bit out of order. So remember, in manual operating procedures, we're looking for a compromise between too high and too low. So what about low altitude? Below 10,000 feet with your traditional manual operator, manual radar. This doesn't apply to the RDR 4000, which has a different philosophy behind it, but for your old RDR 4Bs or for the multi-scan radar in auto, this would be true. Just set a +5 degree up tilt. So +5 degrees keeps the radar pointed up along the aircraft flight path. Everything's pretty reflected down there, assuming it has water in it. And so +5 degrees up tilt is just a good tilt above or below 10,000 feet. So you're really busy during this time frame. You're doing checklists, you're talking on the radios, you've got a lot of stuff going on. So setting the +5 degrees up tilt is the best procedure below 10,000 feet. Above 10,000 feet and up to about 25,000 feet, this mid-altitude weather, what I would recommend is use ground clutter to properly set the tilt. So for the 40 and 80 nautical mile range scales, what you do is you lower the tilt until there's a little bit of clutter in the outer range scale. What this does is it keeps the tilt pointed down into the reflected part of the cell. And what you can do is you can watch the cell as it marches in towards the airplane. As long as it stays on the display until about 20 nautical miles, you know it's probably at your altitude. This is over eastern China right here. It's mountainous, so you don't get the nice solid clutter ring like you do at our home office where it's all flat. But you got the top of the mountains that are setting the clutter ring in this particular case. So 40 and 80 nautical miles use the clutter ring to set the scale. Now, you do have to remember Above 10,000 feet, you got plus 5 degrees up tilt set at 10,000 feet. 10,000 feet is where you have to start applying this 40 and 80 nautical mile range scale clutter ring. Because what I've gone and jump seated with a bunch of guys. One instance I remember in particular, where they set the tilt at 5 degrees up tilt, and they climbed all the way up to cruise altitude, still set plus 5 degrees up tilt, and they're looking into outer space. You know, and there's no way they're going to see weather up there. So at 10,000 feet, that's when you set the clutter ring. You're going to climb further, the clutter ring is going to disappear, so you have to lower the tilt. You're continually lowering the tilt to keep the clutter in the outer range. Does that make sense? Okay. 160 nautical mile range scale is really tricky to set. And the reason is the Earth's surface is curving away. So at 160 nautical miles, the bottom of the radar beam and the Earth's surface are almost parallel to each other. So you can't get a nice solid clutter ring on the 160 nautical mile range scale. So what you do in this particular case is you lower the tilt until the whole display is full of ground clutter. And then you gradually raise the tilt. If you can see it on my computer over here, all over this display there are little green specks, kind of like electronic noise all over the display. That means the edge of the beam is right at the Earth's surface. And anything that pokes up through, like these green things here, that's weather poking up through that noise. So 160 nautical mile range scale, the tilt's going to be higher than either 40 or 80, so it's a strategic weather assessment situation. That's not, you probably want to fly in the 80 nautical mile range scale most of the time, because the 160 nautical mile tilt is going to be a little high. But that's how you set the tilt. Put the ground clutter in there, raise it gradually until you get speckles all over the display. And then anything that pops up out of that is weather. So for high altitude tilt management, 25,000 feet and above, exactly the same procedures work. For 40 and 80 nautical mile range scales, use the clutter rings. And for the 160 nautical mile range scale, use the clutter speckles to set your tilt. Above 25,000 feet, though, that's when you've got to start worrying about these inadvertent thunderstorm top penetrations. So here are a number of things you can do to avoid that. First of all, set the tilt at 80 nautical miles, and then in this top right-hand picture, and watch that cell come in towards the airplane. Over the ocean, if it stays on the display till about 40 nautical miles, it's probably at the aircraft altitude. If you are watching it over land and it stays on the display till about 20 nautical miles, it's probably at the aircraft altitude. So it's a little bit like playing blind man's bluff. You know, you just have to remember where it is and avoid it. Another way you can avoid this is set the clutter ring for 80 nautical miles and then lower the tilt until you set the clutter ring. This is all full of clutter, and the clutter ring is now set for 40 nautical miles, as it is right here. So 40 nautical mile clutter ring is set right here. You can see there's actually a shear effect coming out of that cell of this finger that wasn't visible on the 80 nautical mile range scale. And it's right in the aircraft flight path. And this is a pretty low tilt, so that's probably beneath the aircraft altitude, but it is an indication of potential turbulence as you go through there. So your 80 nautical mile range scale is your good tactical range scale. Your 40 nautical mile range scale prevents inadvertent thunderstorm top penetration. And on the Boeing control panel, the captain can set the 80 nautical mile range scale, and the first operator can select 40, and you can look back and forth between the displays. So the best technique really is to use all three range scales. 80 is the primary range scale, 40 prevents unnecessary or inadvertent thunderstorm top penetration, and 160 provides your strategic weather capability. So switching back and forth between those range scales. And because I like the increased gain that multi-scan gives you in auto mode, I recommend manual max gain. It gives you a much better picture of the weather. And it will also be much more similar to the auto Cal gain position that you're used to. Any questions on that? Now, just like you have to lower the tilt when you climb, you have to raise the tilt as you descend. Sounds obvious, but as you descend, the beam progressively digs into the ground clutter. So I did fly with
one set of pilots, and they set the tilt properly at cruise altitude to send it into the airport, and the Indy got green, and then green and yellow, and green and yellow and red. It was beautiful. It's the most pretty Indy I've ever seen. Absolutely useless for detecting weather because it was all full ground clutter. So you have to raise the tilt, keep it in the outer range scale here. Okay, lastly, as we finish up here today, my guess is in manual mode, with a radar in manual mode, you've never seen weather out at 320 nautical miles. Anybody ever seen weather at 320 in manual? Yeah, I didn't think so. And here's the reason why. Over 320 miles, the Earth's surface is curving down by 65,000 feet. So when you raise the tilt to get it out of the ground clutter, you're actually looking way over the top of the cells out here at 320 nautical miles. You can see weather out at 320 nautical miles with a radar in manual mode. What you do is, remember how you set the tilt at 160? You get clutter, bring it up until just the edge of the beam is at the Earth's surface. That's all the clutter speckles. How wide is the beam? 3 degrees. So if I lower the tilt 1.5 degrees, that means the bottom half of the beam is buried in the ground clutter, and the top half of the beam is poking over the radar horizon and looking at my long-range weather. This is what it looks like in real life. So the radar horizon is right out there at about 200, 240 nautical miles. The bottom half of the beam is buried in the ground clutter, and the top half of the beam is peeking over the horizon looking at that long-range weather. So I realize this is pretty useless because you're really concerned about the weather that's close in, not the weather that's out 300 nautical miles. But it really does work. So sometime when you're out on cruise and you're really bored and don't have anything else to do, try this and you really can see long-range weather out at 300 nautical miles in manual mode. Okay, and so my last marketing slide, I'm going to quit here. I'm 6 minutes early. So any questions as I quit here? Yes?
When's the Airbus user guide coming out? The multi-scan?
So I have a draft copy of the user guide available right now for Airbus. What happened with the user guide is that I wrote the user guide for the new Threat Track software. I was asked to divide that into the V1 and Threat Track in the same manual. So I'm just reorganizing everything right now. The information won't change, but I'm reorganizing it. So that's available right now. And as soon as I have time to actually finish this project, it's not long, it's about a week's worth of time, but I've been on the road for 6 weeks, so I'm falling behind and trying to get the manual finished. That's kind of where I am on the manual right now. Any other questions?
This radar uses position information for a lot of its processing. Where does it derive that from? Is it aircraft derived or is it engineers?
So the question was, the radar uses position information to make a lot of its assessment. Where does it get that information from? It's from the inertial. So way back in the wind shear days, a lot of information was provided to the radar, and one of those input items that was provided was the inertial input. So it's an inertial position.
Not via the FMC. What I'm getting at is if you lose both FMCs, it's not going to lose that position.
No, it would not, because it's. So one of the good things is it wouldn't lose the position info, but one of the bad things is it doesn't get the GPS correction that you get in the FMC. So over a 12 or 14-hour flight, you can actually have inertial drift that can cause some ground clutter leakage at the end of the flight because your inertial position is off from the actual position. So, yeah. Good question. Any others? Well, thanks for your attention. And it's always tough to sit and listen to somebody for 2 hours, so I just really appreciate it. Again, I'll put my contact information back up here. And if you guys would like to be on this, I'm always trying to sell this email list. I realize you guys are getting copies of it, but I'm always looking for direct input and direct communication. So please feel free to send me stuff. What I do is, if I can't answer it myself, I go back to the radar engineers. We evaluate it in real time, And then I put out a response to everybody so that everybody can have that information. So again, thanks very much for your time today.
Thanks very much. Hello.
Try that. Thanks very much, Steve, for coming to see us. Steve, as he said, has been on the road for 6 weeks. It's a long time away from his family. So really appreciate him coming in today to see us. Thanks very much, Steve. Thank you.